Hi, so I'm going to talk about how formal verification can make Solana secure. So in case you don't know what formal verification is, it's really quite established technique where we use rigorous mathematics in order to reason about the code to prove that it is correct. In that sense, what's happening is you take code, you turn it into a mathematical theorem, and then you reason about it using static analysis and symbolic logic to prove that it is correct. It's good for proofs, but it's also good for finding bugs, especially finding really subtle bugs. And that's because if you're doing a proof, the only way the proof will work if there are no bugs. If there are bugs in your code, they will be found, or you won't be able to do the proof. You'll get stuck somewhere, and eventually you figure it out. Now, I have 5 benefits for formal verification, just sort of give you an idea of how it will be used. I'm going to focus on 3, which I think are most important. So the first one is what I just said, that it's really good at finding rare bugs or all kind of edge cases. Unlike other things like traditional testing or fuzzing or property-based testing, it's not based on randomness. So if there is a problem, it will find that problem. Now the second one, and this is something that is often very underappreciated, that even just the whole process of writing a formal specification, figuring out what exactly you want to know about your protocol and how to state it in a concise, rigorous mathematical way, that itself can help you understand the protocol and improve it. So for example, we've recently worked with Manifest Finance on one of their trading protocols, and we did an audit for them based on formal verification. And the thing that they found most interesting is that in the process of it, when we were formalizing this, we had really hard time exactly modeling how rounding works. And in order just to do formal verification, we came up with a much simpler model, and they eventually adopted this model that actually made the protocol more secure, more effective, and easier to verify. And then finally, this extra rigor that you get with formal verification, it makes the protocol more trustworthy. You have formal specifications, you know exactly why the protocol worked. You can show the specifications to whoever is interested. You have proof that is backed up by a tool. You can rerun the tool and always know that the protocol still satisfies the specifications as it was when, for example, it was audited first. Now, why is formal verification important for DeFi? That's a very simple argument. DeFi is a trustless environment with a lot of funds connected to it. So anything that goes wrong in your protocol, you get wrecked, funds disappear. That's something that we want to avoid. And formal verification is the only way to guarantee that the protocol is secure. Now, it's not the only thing that you would do to guarantee, to assure security of your protocol. Of course, you would do testing and fuzzing and all of these traditional things, but with them, you're never quite sure. Formal verification is something that gives you a complete guarantee of security, and so it really has to be part of the solution. Now, I come from Certora, that's what we believe in, that's what we work on, but we have the same feedback from Solana Foundation. Formal verification is something that's important, and we really believe that this has the power of making Solana the most secure ecosystem in the DeFi space. Now, as I said, I come from Certora. We build formal verification tools for DeFi. We also do manual audits and audits backed up by formal verification. We started with Ethereum, and in the last 2 years, we've been working on bringing our products to Solana and doing formal verification in Solana. Now, something that happened even more recently, just this February, is now all of our tools are open source and available. You can follow the link if you want to see the code, if you want to run it locally. This is all possible now. Now, as I said, in addition to building those tools, we actually using them. We're putting what we preach forward. And this is a list of some of our customers for which we've done formal verification-based audits. So we worked with, for example, Jito, Camino, Squad. We did a formal verification of the Solana token extension token 2022. If you want to see what a customer thinks, you can go on Twitter and just look at what they say, or you can look at the audit reports, which are all public. to see what we've actually done. Now, what happens under the hood, where the technology comes in, is this thing called Certora Prover. So Certora Prover is a formal verification tool that works in DeFi and now works on Solana. Now, the way it works is conceptually quite straightforward. An input to it is the source code of your protocol and specifications. What do you want the protocol to do? And then it goes into a prover. It does a lot of static analysis. It does symbolic reasoning. And eventually it either says, everything is great, I have a proof, or something is wrong. And here's the input that you can feed into a protocol to see something that you don't expect. Now, if you've sort of seen Certora before in Ethereum space, what makes the Solana part quite different is that we decided to make the specification language embedded in a programming language. So the specification language in this case is embedded in Rust. It's called Cavalier for Certora verification language for Rust. And it's an open source library that lets you write specifications in the same way as you write your programs. So this makes it a lot easier to maintain specifications as the project evolves, and much easier to understand them because they are in a language that you probably already know if you program on Solana. Now, this is the inside of the prover. I'm not going to go into all the details. There's a lot of work that goes to actually make it work, but I just wanted to point one thing. We made a decision that we're going to work on the SO level. So we work on the SBF, on the actual bytecode. That's what gets into the prover. And especially in the case of Rust, this is really important because the Rust compilation pipeline is extremely complicated. It's quite easy to misconfigure it just a little bit to get a bytecode that's not quite you want. So for example, if you don't enable the right switches, your arithmetic may not be checked for overflow by default, or it will be, or some libraries that you import may or may not be checked. Because we work on the SO level, we sort of get to analyze if anything is wrong just because it was miscompiled, the prover will see that as well. Now, to give you a concrete example, I've squeezed one example of a kind of proof. I mean, this is just simplified as much as possible to fit on one slide. But what you see here is how we would verify a very simple fee computation. It kind of looks like a unit test or a property-based test. The important thing here is that the analysis is done for all possible inputs symbolically. It's not done randomly for just some of the inputs. And what you see here is here at the top, there's a bunch of assumptions. They use this Cavalier assume macro. It's kind of like require, except instead of reverting, it just tells the prover, don't care about what happens in other ranges. So here I'm saying that I want my amount to be greater than 0, and I want my fee to be no more than 10,000 basis points. And then here at the bottom, we have a post condition, an assertion. Again, it looks kind of like a regular assert would look like. What makes it special is that it's being checked for all possible inputs, not just for some. Now, if you've written code like this, if you ever had to do fee computation, and if you look at this one, you immediately notice that something is wrong here, okay? The division that I'm using here is a flooring division, which means if a fee is very little, like 0.5 or something like that, it will round down to 0. And this will violate my property because I want to say if I'm asking for a fee, I want the fee to be something never 0. And so if you give this to the prover, it will find this and say, oh, there is a bug. Here's an input that will cause the overflow to happen, flooring to happen. And if we change it to using proper ceiling division, then everything will be correct, and the prover will prove this rather quickly. So this is how specifications usually look like. Of course, instead of the code for the fee, usually it's a call directly into the contract, and there's a lot more code involved, not just this little few lines. Now, I mentioned that we've successfully applied it to multiple customers. I mean, that shows that it actually works on real significant protocols. I want to highlight two here. One is Camino, and the other one is Manifest Trade, mostly because they are on a very different parts of the spectrum from the point of formal verification, just to give you an idea of what's possible. So Camino, I'm sure you all know, the Camino lending protocol is what we looked at. It's on one hand, very straightforward. It's very well engineered. It does whatever lending protocol does. It keeps information that, the way you usually keep in an account, but its computation is very complex, right? It has to manage all kinds of different fees, all different rates, apply them in a proper way. that part of it makes it really, really complicated, and you really need formal verification to see that everything is done properly. And for this protocol, we focused on the core lending properties. So things like solvency, that says the ratio of assets to shares goes in the right direction. And things like the holy grail of this protocol, that the health of any account is not affected unless something specifically affecting health has happened. So the loan to the LTV just stays in one way. And we also proved things like that liquidation is always profitable. So core properties of the DeFi part of the protocol. And if you want to know more, there's a QR code here to go and look up at the report. Now, the second project is something called Manifest Trade. It's a trading platform on Solana. And what makes this project interesting is that here, a lot of effort is put in order to pack as much information as possible into a single Solana account. They wanted the whole market to be one account for various reasons. And in order to do this, they need to be able to pack a lot of information in an account. All the traders, all the orders, both sides of the book, everything is inside one account. Now, to do this, they created a new data structure that they call a hypertree, which is basically a red-black tree layered on the account space. Now, if you've ever tried to implement a red-black tree or done one maybe at school at some point, you know that on one hand, it's very straightforward. It's a very simple data structure. That's what makes it efficient. On the other hand, it is notoriously hard to get right, simply because it's all about all kind of cases. Specifically, whenever you remove or insert a node, you have to recolor things properly so that you have the right mix of red and black nodes. And that's just given as sort of lots of tables how to do it. And if you get one of them wrong, the tree is going to be miscolored, and that will cause it to be unbalanced. And if you're lucky, it will just cause a loss of performance. If you're unlucky, it may cause more significant problems where the tree will not be ordered. And so what we've done for Manifest is we've shown that their implementation of the red-black tree is exactly an implementation from the algorithms book. And actually, it's something that when we did this, we actually did find an issue with a swap function. So in fact, the coloring wasn't completely right, and the tree could be unbalanced. And this was something that was a very, very difficult edge case to find. They've done a lot of fuzzing before and it wasn't caught by this. And even the example that we construct has to be a pretty large tree in order to find out where this is happening. And we also done, of course, in addition to this structural property, that's sort of from formal verification that were the most interesting, we also done the basic DeFi properties. For example, that no funds are lost, that the accounting, internal accounting is correct, that if you, say, place an order and then you cancel the order, you get the right amount of funds, accounting for rounding that gets back to you. What we see is our mission is to bring what we would call a continuous audit to Solana ecosystem. One of the great benefits of formal verification and audit with it is that it's not just one point in time. You don't just get somebody to look at your code and say, there you go, your code looks good. You have a tool that can run over your code again. So if you change your code, the audit can be rerun and you get to see what happened. If you did a small change and now no property is affected, you're just going to get a green check mark. If you did a big change and maybe you've broken something, you're going to get a counterexample. And if you did a significant change, maybe the whole thing will break and it will tell you, formal verification can tell you that everything is fine. You changed too much. You really need to think more about your properties, or maybe you need another audit. So that's it. So I'm here to tell you that Certura Prover is now on Solana. As far as I know, it is the first and only formal verification tool for Solana. It is open source. And if something that you're interested in, come and talk to me. Come to our booth. Thank you.